I'm currently recording, so thank you everyone for joining us to the open discussion session. This is going to be a bit general about different topics, meaning the first ones that I would like to actually raise were things that were already raised during the other discussions and the seminars, in particular about Stokes phenomena and summation. So what I will do is I will start with a few comments, which will be, I apologize right away because they'll be inaccurate both on the side of the Stokes phenomena and on the side of the hydrodynamics. It's just to try and understand like some parallels and what could be learned from one to the other. For that, let me just actually share my screen. So I hope that you can see my screen. Can you see the screen?
Yeah.
Yeah. Okay, so I will start with some brief comments about what I would like at the moment to perhaps the first questions that I would like to raise to see what people would have to say about how to go ahead with the subjects. And the first one is the fact that we've seen during this week also many examples of parametric asymptotics. What do I mean by parametric asymptotics? I mean that we're studying an observable, either it's the energy density, the pressure anisotropy, well, it's the same thing, but any observable that we can analyze perturbatively, but it also has a dependence on an external parameter. And actually, meaning this can lead to a divergent expansion, and the divergent expansion can be in, for example, for the energy density for large proper time, but there's a parametric dependence on an external parameter, or it can be actually like Ben's talk yesterday for the trans series that he showed, an expansion in a small parameter that is the external parameter in some way. So does parametric asymptotics. And in these cases, we can have the changes in the behavior of the solution, which come from the fact that you have different exponential scales, and because of this dependence on the parameter, the different exponential scales can change dominance, or like as we're going to see in an example, move off to different sheets, for example, and disappear. This is not things that have happened, I think, in the case of hydro, but it's the different types of behavior that could happen if we study such examples. I just want to briefly mention meaning two of the papers, well, from authors in here in the audience that have analyzed such cases. And for example, this is one of them, like it's called why is a shock not a caustic, and the higher order Stokes phenomenon. I'm not going to go into the details at all, but what they analyze in that case is Berger's equation. It's a PDE. It has a small parameter. They include a particular type of initial conditions which have obviously two singularities in X. And one can actually analyze the solutions, and they find that the solutions are, you can solve them perturbatively in epsilon, and what you find is at least two possible like typical contributions that are exponentially small. There's these FJs, which are the omegas, if you want, from the hydro, and there's also a perturbative series. So what I wanted to mention is that in this case, so basically what the paper is about is analyzing caustics related to the fact that you have singularities on the initial data. But the interesting thing that I just wrote here is that what they write is that the identification and location of caustics required simultaneous satisfaction of two conditions: the coalescence of both the real and imaginary parts of an exponent, meaning the FJs. And what you have here in the complex plane, in the real, you have the real part of X, the imaginary part of X, and also the time passing. What you have is like here where where you have the caustics, and basically you can have, so here I think you have that the two in the CRs, you have that the two FJs, so there's two possible FJs here, F1 and F2, that they're the same. Here, when you have the C01 and the C02, they're actually 0 at that point. So you have that there's no, the exponent is 0 in these two cases, and then they move off to a different type of behavior in the C01 and C02. But basically what I'm trying to say is that behavior of these FJs, these exponentially small terms, actually tell us how the behavior and the existence of these caustics come about, especially in the complex plane. I found this interesting just because of all the drawings that we also saw, especially from Ben's analysis, where he does the analysis of the hydro expansion of the omegas of the modes, and how they change, and they can coalesce and become different ones depending on the momentum. So another example of this type of behavior is what was done also in the Pearcey equation, where you basically can do some saddle point analysis on this integral, which is a solution of this differential equation. You have 3 saddles, and a lot of things can happen, meaning this is a drawing of what happens. So you can see that it depends on some external parameter, A, and basically by changing A, you will change the behavior of and the contributions that come from saddle point analysis. And in particular, when you're changing, if you analyze this in the Borel plane, so in the singularities, in how the exponents, the different exponents relate to each other, you can actually see that the exponents can move, meaning meaning this is we have 3 saddles, like I've mentioned, and you can have one saddle kind of moving from the direction made by the 2 other saddles from one point to another. And this can lead to all sorts of different behavior for your series, for your solution, especially because some of these, that means that some of these transient modes, what we would call transient modes, can just basically not stop contributing at all. Or also, if you change the A, they can start being coming closer to the origin or further away. So there's a lot of different behavior here when you have these 3 saddles that can happen, and change the physics of the actual solution. So just finishing this up, then how does this relate to the hydro and the kinetic theory? So, for example, from Ben's talk yesterday, he mentioned the Trans series, and so he's solving a modified telegrapher's equation, which has the small parameter. Of course, for the final problem, you're interested in having epsilon equals to 1, but in this particular case, you're solving this PDE where you have some initial condition. You can do saddle point analysis. You find 3 saddles, meaning that you have this related to having like so this is the solution basically, which has some perturbative expansion, and also some non-hydro mode which starts as exponentially small. You can do some saddle point analysis in the momentum space, and what you find, sorry, not in momentum space. So this is the equation in momentum. This is the equation in X space. You can find the Trans series in momentum space, but then you can do a Fourier integration, and you can do a saddle point analysis there, and you find these 3 saddles. And the interesting thing that I found in the comments there is that you have some coalescence of saddles at particular times. And of course, you can find that Stokes phenomena will depend on the initial data as normal, but it will change in time and space as well. And I would love to understand how these 2 things could be related. What I just spoke to you about, for example, about the Pearcey equation, and in this case about the telegrapher's equation that they've solved. Also, one thing that I would like to mention is, like, from Michał's talk, when he talked about kinetic theory, he also said that you could introduce a parameter, delta, in your theory, where you have that if you take delta to 0, you have just the relaxation time is constant. If you take delta equals 1, is the usual Bjorken flow conformally invariant that you can solve. And what you can get is, like, by varying delta in the Borel plane, basically you can find all these different singularities, and they actually move around the complex plane. You can see the difference for different deltas. Of course, this is for delta real, and the question then, can we see some different behavior if now we start taking delta to be complex? So this is the external parameter. And of course, I would love to understand one more thing, which is basically other examples. So in the paper by Aaron and Christiane, like, for example, can the charge dependence lead to some sort of higher order Stokes phenomena as well? And how does it relate to the convergence of the hydro expansion with the dependence of the charge? And also, meaning there's a few papers on the dependence in large D versus the finite T holography. And my question then is, like, can we see D as an external parameter as well in this type of behavior? Can we do large D asymptotics and see how that would relate to the finite D results that we already have in many different cases? And there's, of course, other examples that you could imagine. So I'd like to stop here for a moment and see what people have to say about this too. So that I would really like to understand how these two approaches, meaning they're not two approaches, but like how, like, what is known from the higher Stokes phenomena community could be used, for example, to understand a bit more about relativistic hydro, and also how relativistic hydro, meaning what are the questions that people want answered in kinetic theory, meaning for example, in the examples I gave, from that could be given by the higher order Stokes. Yes, please just ask questions directly. Chris?
Yeah, can you go back to the telegrapher's equation, please? So the expansion is in terms of epsilon. Why is, rather than tau, what is the difference between epsilon and tau?
So maybe I should, okay. So I don't think, for the telegrapher's equation, I don't think there's any difference. But the way that we introduced epsilon in the paper was motivated by picking a mode. So this telegrapher's equation has a diffusion mode at small k, which, so omega goes like minus ik squared. And that has this scaling property where you scale space by epsilon and time by epsilon squared, and it's invariant. So whenever you have a system with that mode, the idea is that you perform this rescaling, and that mode is a fixed point of that scaling, and everything else is perturbative in or becomes non-perturbative in epsilon. So the idea is this is a general procedure you can apply to any model. You pick the mode of interest. If it's diffusion, you scale t by epsilon squared and x by epsilon in the equations of motion for that system, and then you do the expansion in epsilon. So this was applied to the telegrapher's equation, and it just so happens that that epsilon matches the tau expansion in the telegraphers. But for example, you could do it in holography, but you wouldn't have a single parameter like tau, which would control it. So it's just more of a general prescription. The short answer is yes to the same thing in this particular application.
So sorry, I have another question about this. So originally you didn't have an epsilon, right? So if you go back to your original problem, you should take epsilon equal 1, right?
That's right, yes.
Then what does it mean, the expansion of epsilon in the sense of original problem?
Well, so it's just a formal parameter in order to construct these solutions. And so you would want that.
But originally, this epsilon didn't, it's not included in the original one, right? So
That's
for example,
right. I think
if you,
it's a standard trick you can do in any system you're interested in. If there's a place where you can identify a natural place to insert an epsilon, you do perturbation theory in epsilon, and you set epsilon to 1 at the end. That can get you a long way in many problems. It's about the question is, when epsilon equals 0, is that an interesting point? First of all, it has to be an interesting point to expand around, such that you get a non-trivial solution to the epsilon equals 0 problem, and that buys you something by doing the epsilon perturbation theory. So I think it's a fairly widely used trick.
Also,
okay, but instead of using epsilon, which parameter should be expanded to get a similar solution?
can I just mention one thing? Sorry, this, for example, in all the discussions that we had in the exact WKB, you had a few of the cases that where you did take the H bar expansion with H bar small, and for a lot of problems you were interested in H bar equals 1.
But originally, this kind of Schrödinger equation has H bar, right? From the beginning.
Yes, but you can modify your equation to include a parameter so you can actually analyze it and then still take some kind of approach summation to take it to epsilon to the parameter equals 1. Even if the epsilon parameter itself doesn't have physical meaning.
So an analogous, just an analogy, in the entirety of hydrodynamics, I don't really think there's a good parameter except a fictitious parameter which we introduced to count the number of derivatives. So I think this would be the approach that I would take in looking at the perturbative, looking at hydrodynamics as a perturbative expansion in gradients. You just insert a parameter which counts the number of derivatives. So here we've inserted a parameter which counts time and space derivatives slightly differently, so that when epsilon goes to 0, it's focusing on this diffusion mode. But if you wanted to do this for sound, you would choose one which counts time and space equally. So I think it's I'm not sure we would have much choice for hydrodynamics. I think this is what you would have to do across any hydrodynamic theory in order to do these expansions. So another example is fluid gravity duality. That does exactly the same thing. You introduce a parameter like epsilon, which counts the number of derivatives, and then you set epsilon to 1 at the end.
Okay, but in this case, this epsilon is always coupling with tau, right? So small epsilon means, roughly speaking, small tau.
Yeah, in this telegraphers example, it's the same thing. But the reason we separated them logically was because the method should work for any system, not just the telegraphers equation. So you scale. You take the equation of motion and you scale time by a power of epsilon, and you scale space by a power of epsilon, and that will introduce the appropriate factors of epsilon that you need, such that the mode of interest is perturbative, like these ANs in the bottom left, and the other modes become non-perturbative, so that would be the BNs in the bottom right. So this guarantees that always happens, no matter what system you're looking at. So in holography, you could pick the ANs, they would become perturbative, but you would have infinitely many sectors for BNs, one for each non-hydrodynamic mode. But the equation would not be simply an expansion in tau, because there would be, in holography, what are the parameters? There's no single parameter you would expand in. But epsilon gives you one.
Is my microphone working now?
Oh yeah, yes.
Yeah, I came and left again because clearly it wasn't. Aren't you just doing a large time expansion? I assume the ANs scale with powers of t, right?
It's an expansion which is sort of large T and large X, such that diffusion is a fixed
Yeah, I mean,
point.
it's on the diffusion scaling.
Yeah, exactly.
It was going to be my other comment. If you do the hyperbolic scaling instead,
Yeah.
I started playing around with Liouville green on this, and you get real line turning points at X is plus or minus T rescaled, which is unsurprising because it's the hyperbolic wave speed. So are those turning points?
Sorry?
So on the hyperbolic scaling, there are turning points at X is plus or minus T.
For this same equation for telegraphy?
Yeah.
Okay, yeah.
Which is, as I say, is unsurprising. It's the wave
Right.
speed.
Yeah, exactly.
But I'm not sure if they relate to your turning points because you're on a different, your saddle points.
Yeah,
You're on a different set of scalings.
Yeah, exactly. That would be a completely different expansion that focuses, let's say you were in this, so if you had let's say you were doing a sound, this was shear channel, right, where the hydro mode diffuses. Let's say you were interested in the sound channel. So there you have a mode which propagates, omega goes like K. So then the scaling you're talking about now, that would be entirely appropriate for the sound channel. And that would highlight, so the perturbative sector would be the sound channel sector.
But right, from the point of view of formal asymptotics, the large time behavior has two different scalings in it. So the parabolic scaling and the hyperbolic scaling, and they're both there at the same time.
Right, but only one of those describes the hydrodynamic mode for this equation.
Sure.
Yeah, so it depends. Yeah, it depends if you're interested in the hydrodynamic aspect of it or just more generally. Absolutely. But yes, you're right. So you can, so in no matter which mode that you're interested in, you pick an appropriate scaling for that mode. So it doesn't have to be sound or diffusion. It could be some arbitrary exponent. If your mode so if you had some lift shifts invariant theory, that would, typically have some omega that goes like K to some power Z, where Z is this lift shifts dynamical critical exponent. And
yes, I mean, in the language of my community, there are two distinguished limits. One is the parabolic scaling, one is the hyperbolic, which do capture the entire large time behavior.
Sure, but so there are more exotic physical models in which you see more exotic scalings.
Sure.
Like Z equals 3 or just fractional powers of Z. So in these condensed matter systems, some of them have peculiar fractional powers of Z modes with behaviors that don't look anything like these, and that would be that choice. An appropriate choice of epsilon scaling would work there too, but you'd have to pick the powers correctly.
So one question that I wanted to ask is that, so you write the solution here with just, you have your perturbative epsilon and you have one exponent, but you do have the contribution of three saddles. So how does this come about? So
the saddles are a combined contribution of this piece, this row hat. And inside this row hat, you have the dependence on initial data, and that affects the saddles. So you want to integrate this across K, along the K. You want to do an integral in K, and so both the initial data and these mode frequencies enter it. And so you can see that all of this behavior we talked about, this Stokes phenomenon, is T compared to some scale TC, which is set by the initial data, actually. So TC was S squared, roughly speaking. And S squared was the width of this Gaussian in the initial data. So both of these structures are important, having the quasi-normal mode frequency complex structure, but also what choice you made for initial data. And obviously we picked Gaussian because e to the minus x squared is a very simple thing to turn into a saddle point type integral. But if you had something more complicated, you'd have to exponentiate it. And then I don't know, there may be infinitely many saddles. There may be, I don't know.
But when solving for the actual solution in momentum space, you only have So you really only have two possible solutions, like this exponential and this.
Yeah. So exactly. So I think this trans series you've written in the bottom left, that's it. I think it's completely, there's nothing funny happening. That's just the trans series in general. So it was kind of boring, but the point is that in position space, obviously it's not, it's sort of highly non-trivial to go from this to position space.
I mean, there's one more interesting aspect that at least surprised me when I was, well, I mean, like, as compared to the expectations. So these model, like the telegrapher's equation, like when you solve for eigenfrequencies, like there's going to be two solutions. Like one solution is going to be the hydro mode, like the other one is going to be non-hydro mode in the terminology that Ben uses in his talk. And this the non-hydro mode at large momentum is gonna become propagating. And the interesting thing that happens with these saddles is that one of these real space saddles correspond to behavior that I think is like e to the minus t squared, I guess, right? And this e to the minus t squared, so not like the behavior that you would expect from the transient, like which would be like e to the minus t. This e to the minus t squared comes from the initial conditions that are e to the minus x squared, and that split into wave packets. And the transient behavior that you see is not really, exponential, is not dominantly exponential decay due to the transient nature of the transient mode, but rather it's a wave packet that is receding from you with some velocity. And what you're seeing is that, you're just seeing its tail that gets smaller and smaller. So it's kind of interesting because when I thought about applicability of hydrodynamics, I would say that, hydrodynamics becomes applicable when the transient effects decay exponentially in time. But, if you think about applicability of hydrodynamic at a given position in space and time, it turns out, I mean, like this work revealed, at least to me, that there are two effects that can come on top of each other. Like one is exponential decay, but the other thing is that these transient effects can also propagate. And, they can just propagate away from your position, leading to applicability of hydrodynamics. So, I mean, for me, this is like an interesting practical lesson from the saddle point analysis that was a complete surprise to me. I mean, if one thinks about it a bit longer, I mean, like it should not come as a surprise, but yeah, I mean, like I wanted to highlight it because it might be, buried in the mathematical details. But physically, I think it's an interesting possibility that emerged from this work.
One question that I would have also is, for example, the meaning you do mention that there's a coalescence of saddles. What happens to that exponential? Meaning to the saddles, the saddles become zero, go into the middle point.
I think the actions are zero.
The actions are zero, so they all basically.
Yeah, sorry. I would say that the actions are not zero. So they merge at k equals 0 in the non-hydrodynamic sheet, but the actions are still fine.
But then what does it mean that they coalesce?
That the action of the two saddles which are of the origin become equal to the action of the saddle that's at the origin.
Yeah, sorry, I just looked up my slides from yesterday. Indeed, not zero.
But they become all the same.
Yeah, they appear at the same point with the same action, if I remember correctly.
So I guess another question that I would have is whether anything of this could be, could you see any kind of behavior like? So I guess that from this first case of the Burgers equation, you did have an initial condition which had a singular, some singular points. While your initial condition, I guess, has, meaning it's quite well behaved. But I was just wondering whether meaning you've played around with some of these with initial conditions and how they would behave, and whether you'd have like behaviors, you could have behaviors coming out like this, what they mention in this paper, like the shocks and the caustics, which are related to the definitely the saddles, like in terms of saddles, the saddles coalescing, or the.
But this is a linear equation.
This is a linear. This is a non. I know this is a linear equation, but they have plenty of other equations, meaning that they just linearize, but they're not linear. So here it's a linear equation, but so in general, I think that.
I mean, the local model here is the, I mean, modulo the 2 branch cuts, as long as you don't go near those, and the contribute, depending on what the contributions there are. I mean, the local model is just Pearcey, whereas, you know, Berger's is very different. It's a nonlinear equation. There was, yeah, I take the point that there's a linearization in the particular boundary data that we looked at there that allows it to be locally Pearcey-like. But of course, because it's nonlinear, you do get all the infinite repetitions of the singularities, which are the things, it's that infinite sum of those when you do the trans-series summation that then leads to the shock formation. So, I mean, the question here is, I mean, these are only square root branch cuts, but you can do transformations to turn them into cosines and sines and do it like that and generate infinite numbers of saddle points. And the question is whether they ever accumulate to give you anything shocky, you know, or shock-like. But yeah. And in terms of the initial data, the thing about the initial data is that you've also got, John King will correct me here, but I think John Chapman's looked at this type of problem, as well as, oh gosh, what's his name? Tanvir and co. You know, that you have the singularities in the initial data, they can give birth to daughter singularities, as they're called. I don't know why you use the word daughter, but daughter singularities. And the types, I think, that John Chapman studied, there are 3 types. There's one where you've got the singularity embedded in the initial data, which is what we've got in the Berger's. But then there's other ones where you have no singularities at t equals 0, but at t equals 0 plus, those singularities can come in and stream in, and then that gives you these caustic-like behaviors coming in from infinity rather than from the finite positions in the initial data. So, I mean, I'm just throwing that into the mix to confuse things, but and obviously you can also have scenarios where you have no initial singularities that never generate anything, and that's kind of the boring stuff. But.
So I guess then my question is, so this is a very simplified model, as you mentioned, Ben. What would be the next step? Of making it, because of course because it's overly simplified, it has issues, and you would have corrections to it. What type of corrections would you start adding?
I guess it just depends on what your main concerns are. So if you were concerned about the linearity, then obviously trying to, even within MIS, you could start to consider what the nonlinear corrections would do. I have absolutely no idea how feasible that is as a calculation. You could also wonder about how special the model is. So MIS is obviously one of these toy models that should not be taken particularly seriously. And so moving towards something like holography might be a good idea, but and in many ways, you know, fluid gravity is an incarnation of this epsilon scaling, where you choose time and space to be scaled the same way. So if one could move towards constructing non-perturbative contributions within the fluid gravity map, that would be, I think, very nice. I would love to see that. I don't have a good idea about how you would go about doing it. Yeah. I don't know if any other thoughts.
And also, I had mentioned briefly this example when Michał spoke about it very quickly in his talk. So, of course, we're interested in the delta real, but just as an understanding of how these singularities actually come about and whether we can expect them to always contribute or not. I think that it could be quite interesting to just understand how, not just how they vary for like in modulus, but also how they would vary in the complex delta plane, just to understand whether there's extra interesting behavior showing up there. And you mentioned, Michał, that you had that there could be some actual analytic expressions for some of this.
So unfortunately, I don't remember exactly if we do have analytic expressions. Like for low orders, for sure, like you can get analytic expressions, but the question is like you can have it like up to the useful order. I mean, like maybe Victor, if he's in the audience, remembers this. But this,
yeah, only a few orders analytically in delta, not too many.
But numerically, like let's see, numerically, I'm not sure. I'm like, I would not expect like to have problems in generating delta that is complex. I'm like, sorry, generating the low orders, like some number of orders numerically for complex delta. Do you, Victor?
No, I think that should be doable.
Yeah.
And also, meaning you have the expression of the exponentials, meaning this delta E that you've written, which has some of this behavior. I guess these exponentials would be the branch points that would show up in the Borel plane, right?
Yeah. So this is the formula for the position of these off real axis singularities as a function of delta, right? But I would, yeah, like I think like the simplest thing probably to do would be to assume that this formula works also for complex delta. I mean, like here, well, maybe actually this formula works even for complex delta, like without assuming it. And then you can just play with it, right? And try to see what comes out. I guess like what might be interesting is to see maybe like if the singularities coalesce for some value of delta, right?
Yes.
Because what we observe
cross paths.
Yeah, exactly. So what we observe is that the absolute value of these decay rates or frequencies or whatever you want to call them, they can be equal to each other for some value of real delta. But of course, like the real and imaginary values are still different, right? And you can see it here in this figure, right? Mm-hmm. That like one singularity stays always on the real axis at where it wants to be, and like the other two, like are moving as a function of delta, so they never touch each other, right?
Yep.
But yeah, I mean, I guess like since the other one is at 1, like the thing to do would be probably to see if there are interesting solutions in which this guy over here is equal to -1, right? Like the question is like, what is the delta? Right? Like it's gonna be complex delta. Because if this happens, then like these singularities, like they go here. So this one, I mean, it clearly stays where it wants to stay.
It doesn't move, right? It's constant.
No. The nature of the branch cut, like the information code in the branch cut probably is delta dependent, but like the position of the singularity is not.
Sorry, I have another question. So maybe in this problem, you had a differential equation, right?
Well, like in this problem, like you either have a Boltzmann equation, or you have like this integral equation that goes in the name of Beim equation. So like one of the two, I think. And the Boltzmann equation is a partial differential equation, but the problem is that you have to, when you do calculations, you have to impose Landau matching condition. I guess, and like when you do this, no, sorry, like you have to, yeah, I mean, like you have to impose Landau matching in the form that it's a RT. So the collisional kernel in this case is proportional to your distribution function, difference between your distribution function and the equilibrium distribution function. And the equilibrium distribution function depends on the local energy density. Mm-hmm. And local energy density is a non-trivial functional of the distribution function, right? Mm. That is given by an average, like, like by taking like a second moment, basically, right? Mm-hmm. What I'm saying is that even the Boltzmann equation itself is not just, I mean, in this case where the collisional kernel is given by a difference of, your distribution function and an equilibrium distribution function, it doesn't involve any explicit integration. So it's a partial differential equation, but because of this condition of RTA that you are supposed to relax to an equilibrium at a given energy scale or like given temperature, you have an implicit moment of the distribution function. So the relation is not that simple, actually. You can still very efficiently solve it to very high orders, but it's not that the problem reduces to a problem of a differential equation of any finite order or of just a PDE.
Okay, I see.
And the other equation, I mean, one can take it from the original paper, but I'm not sure it's the point is here. Like the other equation basically has a form. The other formulation of the problem has a form, and I tried to display it when Mauricio was asking his question, something like this. Then there's like there's some integration kernel. Let's call it like it depends on t and t prime. You have some functional of the temperature as a function of t prime that I don't remember. You integrate over dt prime, and this equals to some other functional of like a probably polynomial of t of tau. Like this is how you can write it, where t is like the effective temperature. So like you have like this partial, like the integral equation that you have to solve. So you can try to formulate this integral equation as a differential equation of infinite order, whatever it really means. Yeah, and like it took us at least like from my perspective a very long time to deal with to solve this setup because it's precisely because of the reason that it's not a differential equation. It's either like this integral equation that I wrote here that you can find in the original paper, or it's a Boltzmann equation with a non-trivial condition imposed on what you mean by equilibrium temperature.
Okay, yeah, thank you.
Just to remember that when you wrote that there was the H and the F, but meaning those functions are related, right? So
yeah, like maybe let's see.
No, but it's I that's what I remember at least. But it's.
Well, we can display the equation, right?
I didn't write it. Sorry.
No, I'm just looking for the paper. Yeah, I'm not sure it's going to be. Let's see. Can I try to share my screen as well?
I
Or-
believe so. If you can't, you directly, I'll stop sharing mine.
Oh, I can, yeah. Yeah, so like this is the equation. So I'm just showing the paper that we wrote with Victor. So like this is the integral equation. Epsilon of tau is the energy density. So like you can either use epsilon of tau, or you can write it as the temperature of time to the 4th power. So that doesn't matter, right? Then epsilon naught is something that depends on the initial distribution function, and it's just a function of time. You compute it like once somebody gives you like the initial data that they are interested in. And this is the integral equation part where you have integration kernel. Like there's some function that has a complicated analytic structure, and like this this is basically the reason for this this is the reason for these additional singularities that we see. What you integrate is like energy density. So like the energy density at a given time depends on the full history of energy densities. And the energy density appears not only here under the integral, outside the integral, but there's also like this additional function entering the equation. And this function depends on the integrated relaxation time. So when delta equal to 0, in this, like in what Ines was showing, like this is very simple. Like the relaxation time then is constant. So like this is just like exponent of t minus t1 minus t2 minus t1 minus t2. But like when the relaxation time depends on the effective temperature, so on energy density, so when delta is non-zero, then like energy density also appears like inside an integral in 2 more places. So it's a very sort of subtle equation to consider. And then like there's an integral, and this integral is taken along the real axis. And these additional singularities that we see in the Borel plane for the hydrodynamic gradient expansion, they have to do with possibilities, mathematically speaking, of contour deformations of this integral away from real axis in such a way that you sort of include contributions from singularities of this function. I mean, this is the best understanding that we had of these additional singularities, and we never really went any far. At least on my side, like I never really went any farther in understanding them. Like that was like completely satisfactory for me. So coming back to Syukamata's question, I mean, it's this problem was so exotic as compared to other stuff that was studied. That I'm like the methods that were developed, like for some of the methods that were, or some of the intuitions that were appropriate for the other cases, like did not really apply here.
So just quickly before, going to asking for Coach's contribution, I just wanted to mention that, well, of course, meaning I think I will leave this as different options, meaning of also parametric dependence in hydro, which I could really I'd really love to see how like the parameters actually play a role in asymptotics and in the actual solution in the end of the observables. But I just wanted to mention one other open thing, which, of course, meaning if you're trying to do this trans series and asymptotics in a lot of cases, you're doing it in one regime, like which is late times when things are already like followed towards an attractor solution of some sort, or the transient modes have disappeared. But of course, it's a big question of how to connect that to the initial data, because the initial data has basically, it doesn't contribute to this late time behavior. So one of the things that Mauricio's work has shown is that you can use in some way the summation of transasymptotics to get close to it. But still an open problem, of course, is how to really handle this properly, and also especially in holography when you can have multiple parameters, of course, make the match between the two things. And I guess my question in here is that whether people have thought about, like, through other methods as well, that could even help understanding a bit better how to do this match through transasymptotics, how one can still see some like, so in conformal theories, from what I understand, you don't see evidence of the initial data once you get to the large time. Is this correct?
In what sense?
Meaning that that you could have different initial data, but the late time expansion would be the same.
So for the Birken flow, right, like if you use this W variable, then for conformal situations that we know and love, right, like there is no trace of initial conditions. If you use like the tau, like the proper time variable, there is a single trace of initial conditions, which basically corresponds to the final amount of entropy per unit rapidity. Like this is like often referred to as like a capital lambda parameter in the literature. Now, what happens like outside the conformal situation, that's been very little studied. I mean, like probably like almost non-existent. So I'm from the point of a lot of the asymptotics. So I'm not really sure what to expect.
Okay, well, okay, so in this kind of the scaling invariant case, the W is good parameter because it's a scaling invariant quantity, right? So in this case, the part of the expansion doesn't have the dependence of the integration constant, but once you go back to tau coordinate, so this power law has a dependence of the integration constant coming from the equation of T. So yeah, maybe if you go
this is precisely what I wanted to say. Yes.
Yeah. So in this sense, if you break the scaling invariant symmetry, then yeah, probably, yeah, you should take care of the propagation of the integration constant coming from T, I guess.
So would that kind of meaning, because so at the moment, in terms when you have scale invariance, then I mean, the only way to make contact with the initial times is having some kind of an approximation for the parameter that shows up in the transasymptotics. But if you did go beyond that, maybe there would be other ways of using the information of initial data that would kind of fix the parameters in the transasymptotic summation without having to do this fit. Would this be a possibility?
Yeah, I don't know precisely. So yeah,
I honestly don't know the answer. I have no idea if the answer can be known. I'm just wondering. Sorry, just things out there that have been used. Like these summations that are quite efficient, but I guess beyond the scale invariant case, not much is known, I guess.
But you mean like the summation of the trans series and matching to the initial condition? This is what you want to do?
Sorry?
You want to sum like the trans series and match to the initial conditions, like this is what you want to do?
Well, they did do this, right? They did not from Borel plane point of, not Borel summation point of view, but they did the transasymptotics, and they try to fix the trans series parameter such that, meaning with a fit. But again, I think this is a situation where the only glimpse of initial conditions that you have is actually by going at the early times. And my question, I guess, is more that whether, like, okay, if you break scale invariance, whether there would be other ways of getting information about the initial conditions that wouldn't require you to go to early times, just so that you could still fix your parameters, but without having beyond many.
You basically would like to see like the information about the initial conditions sitting in a a zero level of transseries in the perturbative part of the transseries, something like this.
Yeah.
Okay. Yeah, so apart from this lambda in the Bjorken flow, I've never seen anything else.
But I guess that would be my question, my general question, whether there would be ways of or any model where one could try and explore this type of questions.
Ines,
Yep.
first, concerning this point, because in a way, this power series part of the answer, which is just a hydrodynamic part. So basically, what enters there are all the arbitrary parameters which are necessary to specify the hydrodynamic solution. So in the case of Bjorken flow, just a single parameter, the lambda, because this is just the only parameter which is necessary to completely specify hydrodynamic solution with the assumed symmetries, right? So no dependence on transverse variables and boost invariance. However, if one relax those symmetry arguments, those symmetry assumptions, then I guess that, of course, there are lots of various hydrodynamic solutions, right, which would depend really on full set of parameters, in fact, an infinite number of parameters. And all those would appear as parameters in this power series part of the solution. So, so generally, I guess you would have lots of parameters specifying the power series like part of the solution, but of course there will be further additional parameters in this trans series which would come from quasi-normal modes and stuff like that. So the simplicity was, I would say, just an accident of the symmetry assumptions of Bjorken flow.
Okay.
So in the last part of Ben's talk, like he talked about this Fourier space analysis, right? Like of the gradient expansion. So like the gradient expansion that he meant was like a purely spatial gradient expansion, but like how it looks like is going to depend on the Fourier decomposition of initial conditions. So like this precisely realizes like what you're saying, that how you initialize your hydrodynamic solution, like, you know, like all these parameters are going to appear one way or the other in the form of how the gradient expansion behaves, right?
Mm-hmm.
But like, for example, the convergence is convergence criterion seems to be related to, I mean, is related to the supporting momentum, like where you cut the supporting momentum with respect to this critical momentum having to do with the hydro and non-hydro mode collision. But if you look deeper into finer features, I think that you can reconstruct more about the initial condition.
Okay.
That's a very good point.
Thank you. I would say that at the moment I would, Goche, would you like to join in?
Yes.
Sorry.
Okay. So yeah, there are a couple of things that I am puzzled about. I think other people are puzzled about as well. And just share a few questions and see what people think. Let me share. Okay. Let me. Oh no. Okay. Do you see my screen?
Yep.
All right. So the major question that I want to ask is under which conditions? So we're talking about the larger the behavior of the gradient expansion and trans series and all that. And in there, oh, did I lose it?
It's
There's a
gone.
yeah. Hold on. I think there's a bit of a action issue. Let me try again. Oh, okay. I mean, right. So, and there are many examples where the hydrodynamic gradient expansion or sort of expansion in some parameter like the proper time or this W variable that Mikhail introduced diverges, and we have some trans-series structure, and we in certain cases we can identify the instantons of this sort of gradient expansion in terms of exponentially decaying modes and so on and so forth. But so this is sort of, you know, it started with the paper by Mikhail and Spilinsky, and there are many examples that I didn't write here, but this whole week of this workshop is dedicated to such examples. But I want to rather focus on focus on two examples where the hydrodynamic gradient expansion is actually convergent. There are these two papers. And in general, sort of my question is, what determines the hydrodynamic expansion, the gradient expansion to be convergent or divergent? What does it mean? So in the cases where it's divergent, we understand, as I said, what the instantons are and so on, but when it becomes convergent, then what happens to those non-perturbative sectors, and are these examples where the expansion is convergent rather some specific cases where the instantons disappear for some special reason, or they're generic as well. So let me just briefly, like in order to set the discussion, talk a little bit about the general structure of the gradient expansion. So hydrodynamics is basically sort of conservation laws on steroids, right? So in long wavelengths, the only degrees of freedom that are of interest are the conserved modes, and the hydrodynamic equations can be written as a conservation equation. So we have, let's say, some density and some current associated with it, and then we have DTFO plus J equals 0. So, and basically in hydrodynamics, we also have an expression in terms of J, expression of the associated current in terms of the conserved density. And what's also common is that we can also express the density as a function of some other hydrodynamic variable. For instance, this could be, if this is a conserved charge density, what I call phi could be the chemical potential, the thermodynamic pair, and so on and so forth. And then the current will be some functional of phi, derivatives of phi, and so on and so forth. So the gradient expansion comes from this identification of the current in terms of phi and its derivatives. And sort of the naive expectation is that so as you go higher and higher orders in the derivative expansion, just because you have many combinations that you can make out of these gradients. For instance, you know, in first order gradients, because J is a vector, you can only have such kind of term. In second order, you know, higher orders, you can have things like phi or some combinations, you know. Things like this. And as you include more and more derivatives, you go higher and higher orders in this expansion. Just combinatorically, you can have many combinations. So the number of terms you might expect to grow factorially, and therefore leading to an asymptotic series. Right? So
one comment about it, like just
yeah, it's just a naive thing. Yeah, but yeah.
So it's not actually what is seen in the linear response theory. I mean, like one can be very explicit, and one does not see the factorial growth of number of terms, as Ben said on Thursday. Rather, there's still a possibility of factorial divergence of the on-shell gradient expansion, but this comes rather from non-factorially growing number of contributions. I mean, like there are like just one or two terms contributing, and these terms on shell just behave like in factorial.
I see. Okay, so that, yeah, thanks. Good. And right. And what let me start with the first paper, the first demo paper. What they showed was that in a relativistic, in a holographic system, and typically, of course, in many cases, going to higher and higher orders in the derivative expansion is sort of is very difficult, because each of these coefficients, each of these terms will come with some transport coefficients, which then have to be input somehow into the expansion. They have to be computed from the microscopic theory, such as viscosities and higher orders of the transport coefficients and so on and so forth. And typically these are very difficult to compute beyond beyond viscosities. However, in holography, it's not the case, and it is possible to go to arbitrarily large orders, these numerically, but of course, in these holographic models, all these coefficients, higher order viscosities, take very specific values. Right. Right. So the idea here, so what they have done is this. So in general, in hydrodynamics, of course, you can have you do have not one but several conserved quantities, several sort of charge densities and associated fluxes, like the energy momentum tensor and so on and so forth. So basically, so you have some number of conserved quantities and some associated currents associated, and then several conservation equations. For instance, in standard sort of relativistic hydrodynamics, you can have T mu and extra current. So the components of the energy momentum tensor, you can view it as separate conserved quantities, energy density and momentum density. And then you also have the zero, and you can have multiple currents as well. And you can linearize these equations and look at the sort of the dispersion relation. So then if you linearize around some solution, perhaps phi equals 0, and look at the equation, the linearized equation, it has some form where Mij 0, this matrix Mij depends on frequency and the wave vector. And if there's if the system is homogeneous, it's going to be Q squared. Then you can obtain the dispersion relation. Right. And you can solve this equation to obtain omega as a function of Q. And what the question that these folks asked is that whether this expansion is convergent or divergent, and they found the convergent expansion. So one remark that I should make is that it is even in very trivial examples, it is the case that a function might be convergent in, let's say, a variable omega or q, but divergent in the Fourier component, right? You can take, let's say, a Euclidean propagator of a free particle. And so the Euclidean propagator, so this is just a remark. So small, let's say small omega versus large T expansions. So one of them, even though it probes the same physical regime, one might be convergent and one might be divergent. For instance, in Carl's examples and many other examples of these expanding systems, it's an expansion in large tau. Whereas in Fourier space, it might look very different. So if you, for instance, take a scalar propagator, plus m squared, which is clearly convergent around Q equals 0, but in X space, with some Bessel function. And Q, and if you so small Q expansion physically is equivalent to large X expansion, which is simple. So even at that level, there is some non-trivial structure in terms of regarding convergence and divergence. But anyway, let's proceed. So and then this problem in holography, solving for the dispersion relation, can be mapped to solving the quasi-normal mode spectrum of a black brane, which basically boils down and to solving some second order equation, which sort of looks like a Schrodinger equation, where you have some functions of so here the variable is u, c. So these derivatives are derivatives with respect to parameter u, and this also depends on omega and q. So So 0. And I don't remember the exact forms of these functions, but they're sort of some rational functions of omega and q and u. They're sort of rather simple functions. Okay. And then we have we focus on the boundary condition where around u equals 1, c behaves like 1 minus u. Let's see. So there's some omega here. I think there's 2 parts here. Something like this. I might be mistaking it. Power, but this is sort of the inflowing on the condition, and then we expand around u equals 0. This has some other function of 1, and some function of this is around u equals 0. And this is the behavior now. Okay. And the dispersion relation, this condition, follows from identifying the diversity boundary. So gives you the dispersion. Okay. And it is possible to generate arbitrarily large number of terms in this expansion, and what they find is that for both shear and sound modes, so the shear mode goes as minus some diffusion constant and q square, and then sound mode the sound mode also has some propagating part. So there's sound. And then there's some specific damping. There's some right, and then dot 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 dot. Yeah, right. So and they find that in fact these dot dot dots for both modes are convergent, and the radius of convergence is determined. So is a convergent series. And furthermore, the radius of convergence is determined by the point where the quasi-normal modes exhibit level crossing, and this sort of, if you borrow the language, sort of the quantum mechanics language, if you view this as some form of Schrödinger equation, right? So there are certain points where some complex values of q squared, the two quasi-normal modes cross. So this is the first example of where we have a convergent derivative expansion, and the second one, this is number 1, and the second example is this is by well, one might think, well, okay, so this is and by the way, there was also well, Mikhail and Spolensky studied again a holographic system, with sort of uniform expansion, Bjorken type expansion, where the large tau expansion is divergent, right? So it's a very similar system, holographic system, where you have convergent series, but the parameters are different. Also, this is a Fourier space, and this is the expansion in Q in terms of Q and omega. Perhaps again, there's a phenomenon which is similar to this. What happens with the propagators? On the one hand, you have a divergent expansion, and on the other hand, you have a convergent one. So it could be. But there's another example by Denicol and Noronha, which looks at a very similar system as the Israel-Stewart type uniform expansion. And here, the setup is that we have a system that expands homogeneously in proper time. So if we have, so this was sort of, this goes back to, of course, the work of Bjorken, and the idea is that suppose we have a heavy ion collision, the ions collide, and after the expansion, after the collision, it creates a fireball, and this fireball expands in the beam direction, beam axis direction, also in the transverse direction. But you can reduce this problem or simplify to a 1+1 dimensional problem where the system expands in just in proper time. So we can, if we draw this sort of light cone, so we have this. And we can work in instead of sort of lab time in proper time, and the energy density as the system expands, of course, the energy density sort of decreases with tau, and that is captured by this. We have the tau, so we look at the energy density. So we have tau dependence, and there's some coefficient here, I think it's 4 epsilon. And then we also have some viscous. Right. And the Israel-Stewart in the Israel-Stewart formalism, the viscous part is also a dynamical variable which relaxes with some relaxation time, and also obeys some differential equation. This so there's a relaxation part, there's a quadratic part. There's something again, tau, and then something like this. Where there are some natural coefficients here, but right. So in the again in this paper by Carl and Carl, they looked at this system where these coefficients were determined by the transport coefficients obtained from holography, where they're all these are all related to each other.
Sorry. So wait. Is it pi square over tau? No.
Pi squared over tau. Is that pi squared over tau?
Maybe, as far as I remember.
No, pi squared doesn't have 1 over tau. So the pi terms have 1 over tau. There's a viscosity. I think pi squared is just pi squared. So I don't know. Mikhail, help me out here. I don't think there's a tau here. Let me pull out the paper. Okay. No, there's no tau.
Okay.
All right. So and oh wait, then but I think if you yeah, if you I think in some cases pi over tau is defined as something else. And in this variable might have yeah, I think maybe it's just the way that these functions are defined. All right, so and again, so in this example, we look at the large tau expansion, and the large tau expansion is sort of loosely speaking. Okay, and then Denicola and Noronha looked at a very similar system, which I think has more or less the same functional form, but with the different coefficients. And this system is again a one-dimensional expansion, where you have just hard spheres, okay, and you can calculate sort of from kinetic theory. You can calculate these relaxation time and some of these parameters, which are different from the Hiller-Sperlinski example. And in this case, they showed that this system has a convergent large tau expansion. So, and this is remarkable in the sense that it's not clearly this convergence divergence issue is not whether you're looking at different sort of Fourier conjugates, frequency versus time. It's the same proper time, same variable, just it seems I think it's the same equation. Maybe there's, I think the functional form is the same, but the coefficients are different. That has to be checked.
So, excuse me.
Yeah.
Probably in the second equation, it has a two IR fixed point, right? So which fixed point are you talking about?
Sorry, say that again.
Okay, so in the second equation, like tau pi times pi dot equals something. So it has probably two the IR fixed point, right? And maybe it's a 0 and plus 1 minus 1. Maybe it's 0. Yeah, minus pi plus pi square is 0. So it's a kind of the IR fixed point.
Right.
So which the fixed point are you talking about?
Which fixed point am I talking about? That's a good question. So in the what Mikhail does is to sort of change variables and define the W variable, and that sort of transforms this equation into something different. And in that language, I don't know actually. Is Mikhail here? Yeah.
So what's the exact question?
Which IR fixed point? So if you look, he's saying if you look at here, I have two fixed points.
Yeah. No, I'm not sure. And I think the important thing here is that, or like one feature of this expansion is that, I mean, in their case, the effective relaxation time behaves like tau, I think. So the expansion is just like an expansion in some numbers. Like there's no tau dependence. I mean, it's like it's a very peculiar example, and I think, I mean, actually, Alex Cervantes might be showing some more results that try to, you know, go outside like this this example and try to see like try to understand what's happening here in a broader context, right? Because
sorry, yeah, I was going to make that precise comment that you're making now. So this system is special in the sense that the Nansen number is a time-independent constant, and the gradient expansion that considered is an expansion basically in this Nansen number, which is time-independent, and they talk about the gradient expansion of the normalized pressure anisotropy, I think, in terms of this time-independent Nansen number, and there's where they find the geometrically growing and not factorially growing character, if I remember correctly.
Yeah, I think it's geometrically growing. And so, what's the sort of roughly the physical sort of explanation?
Yeah, so I would say that this system, I agree with you in that as far as I remember, because I did this computation a little while ago, these equations of motion are precisely the same as conformal BRS3 theory. What changes is the scaling of the transport coefficients with the fluid variables, right? So in particular here, you have a conserved particle current. So you have a particle density, right? So the particle density would scale like the inverse of the proper time, and the relaxation time is not fixed by the temperature in this example, it's fixed by the particle density. So as Michal said, it's proportional to tau. So that's the reason the Nansen number is time independent, right?
I see.
Right. So in my talk, in my next discussion session, I'm going to discuss this particular system, but in the context of the gradient expansion of the constitutive relations, using this formal epsilon parameter that was mentioned before during the discussion session. And I would say that based on the information that I have so far, that the main reason that, first of all, in that example, in that construction, in that particular kind of gradient expansion that I'm going to consider, you can show that Bjorken flow still gives you something that is geometrically growing and can converge. But I would say that the reason behind that is precisely the particular dependence of the relaxation time on the particle density, and also the particular dependence of the particle density on proper time. And once that is broken, either way, either because you consider a more general fluid flow than Bjorken, or because you consider Bjorken, but you change the scaling of tau pi with them, then this property, at least in my construction, in the construction I'm going to be reviewing, would disappear. The factorial growth would kick back in, basically. So that was the comment that I wanted to make regarding.
I see. So you're I see. You're saying the difference is in the two examples. So it's not just that these coefficients are different, but the tau pi tau pi is.
Tau pi has a different, yeah, because you have this extra
Okay.
U1 current, U1 conserved current, and tau pi depends on the particle, on the the density associated to the particular current. Yeah, so I think that the crucial difference comes between the two cases comes from the scaling of this particular transport coefficient.
Yeah. So the tau pi scales with tau or not. So that's the difference. Right?
Yeah, so tau pi here scales with tau, but
Yeah.
the Nunsen number, which you would build out of this, in this system, the natural Nunsen number you can define, which I think it was the mean free path, which is 1 over the particle density times the cross section, which is a constant.
Yeah.
That's proportional to tau. So yeah, so the Nunsen number is that over tau, so it's time independent. So that's a very important. I think that's a very important difference between this system and the standard conformal BRS3, which follows from the scaling of tau pi.
I see.
But of course, I don't know if George is here. Probably not. Otherwise, he would have something.
It's very early and
Yeah. I know that it's also very
yeah, I see. Yeah, so it's right. It's basically whether you sort of
so
it's a big difference. Yeah, it's actually a big difference. Think about it. How you
yeah. So I will mention that I will discuss this some other 1+1 longitudinal flow, not necessarily Boost invariant in the system, and well, I'm going to show it in the discussion session. I have some slides, regarding this very matter, and you're going to see that the geometric growth is going to disappear.
All right. But then it's do you understand why? So when you scale the relaxation time with tau, so in the divergent case, we know sort of we understand why it diverges.
Yeah.
Because we have these exponentially damped modes, which sort of which are non-perturbative sort of contributions to the time revolution. Once you scale that, yeah, it might be sort of rather trivial that maybe if you scale the relaxation time, those exponentially decaying modes just don't exist.
Okay, I haven't thought very deeply about this point already, but I have to say that if you look at the, let's say, the form of the pressure anisotropy, this chi function they mentioned in the paper, yeah, if you look at these objects, they basically involve the solutions themselves basically involve power loss in tau, right? Yeah. So I think that in combination with the scaling of the proper time with tau also brings the difference basically in the convergence properties.
I see. So in this case, it would be safe to say, or it would be the right interpretation if I said, well, if you scale relaxation time and with tau, then those exponentially decaying modes that used to happen, you used to show up in the original equation of
I would say so. I think that what appears in, well, I'm going to talk a little bit about this. So what appears in the exponent in the Bjorken flow case seems to be given by an integral along the flow, right? So it's an integral in tau of 1 over the relaxation time of the local tau, right? So relaxation time is proportional to tau. You basically have a d tau over tau, which is a log. So that exponential term just becomes a power law.
Right.
But that's a very peculiar feature of the system, right?
Yeah.
It relies on the very exact scaling of tau pi with n and the exact scaling of n with tau, which gives you this tau pi proportional to tau exactly. I think if you break that, this property would disappear.
So it's almost like some fine tuning where you kill off all the.
Yeah, that's basically the term I was going to use in the talk. Yeah.
I see. Okay. So that demystifies this question, and yeah, about this general structure of the gradient expansion. So one question which is not obvious to me, at least, is that this work of Donald et al. On the holographic setting. So is this a very particular gradient expansion, because that comes from a very specific holographic system, which probably is a very, it's a very special microscopic theory, which may or may not be representative of the generic type gradient expansion. So is it tied to the fact that it's a holographic system, or is it fairly general? And if you look at the dispersion relation as opposed to large tau type behavior, where the expectation would be that it's a convergent series. Yeah, I think these are the, or whether the gradient expansion is convergent or divergent is sort of not a generic feature of hydrodynamics.
Yeah, so I think Ben talked about Ben's talk yesterday revolves around this topic. So maybe if he's around, he can make some comments on this.
I was just going to ask if you watched my talk yesterday. Yeah, we spent most of the talk was about this.
Yeah, sorry, that's one thing I had a long drive yesterday, so
okay.
Well, I didn't get to watch it. So if you answered it, it's great.
Yeah, it's just so the convergence of quasi-normal modes appears to be generic, that they converge with a finite radius in omega as a function of k. And we've seen that across many models, holographic models, and it's also true in these MIS or BRS3 type models. In kinetic theory and RTA, it's also the case. Yeah, so in every case we've looked at, there's always a finite radius of convergence of omega of k. And in this talk I gave yesterday, I explain how you can relate that to the convergence properties in position space of T mu nu of the currents. So they're actually intimately related, the convergence properties of omega and the convergence properties of T as in position space.
So what's the statement?
So the statement is simplest to make in the linearized context. So the nonlinear context, Alex will discuss in his session this afternoon. But in the linearized context, the statement is that if you have initial data for your time evolution, which has bounded support in momentum space, so compact support in momentum space, then, so let's say it's compactly supported up to some momentum k max, then the question is whether k max is greater than or less than the radius of convergence of the hydrodynamic of the omega of k. If it's less than the radius of convergence of the omega of k, which is set by a branch point singularity, it's not this level crossing that you mentioned, then the series is convergent. And if k is greater than the branch point singularity, it's a divergent series. So there's this very close connection between how much momentum you have in your initial data compared with this critical momentum you can extract from the dispersion relations.
Okay. And do you know? So the divergence of the series would imply non-perturbative sectors. So what happens when you cross that point where the convergent series become asymptotic?
Yeah, so we only, you mean in terms of constructing a trans series, that kind of thing?
Yeah, so how do the non-perturbative how does the non-perturbative sector just arises as you change the...
So what? Okay, so there are multiple aspects of this. So one of them is what sets the radius of convergence of omega of k in the first place? So what happens is the hydrodynamic mode is one sheet of this omega of k, and then there's another mode which is a non-hydrodynamic mode, and they intersect at this branch point, and that sets the radius of omega of k. So the existence of these non-hydrodynamic modes, these exponentially decaying modes, are responsible for the convergence of the radius of convergence for omega of k. They're also the ones responsible for the, in position space, non-perturbative contributions. They appear, so that they, you know, that's two sides of the same coin. And we have a,
you're saying so that before level crossing, you just don't see them in the
for a trans series.
Yeah.
You mean?
For the trans series.
They exist. So if you pick initial data which contain, there's a sort of a hydrodynamic part. So in the linear theory, you can decompose the initial data into hydrodynamic data and non-hydrodynamic data, roughly speaking. And so if your initial data contains non-hydrodynamic data, even at low k, then you will have these other contributions. But they will be both convergent. Yeah, so is there any other statement that we can make?
So can you just explain one thing? So that you're saying that if you try to organize it in form of like hydrodynamic contributions plus non-hydrodynamic contributions, if they were there and you did a series, they would be convergent series.
If the momentum was bounded by this k max, this k star, this critical momentum, which sets the convergence of the dispersion relation. So even below that, you can have very low momentum solutions, which in which you both have hydrodynamic and non-hydrodynamic modes excited, because you remember, you know, you were to draw this dispersion relation, you have two modes, and they pinch off at the branch point, roughly speaking. So at low k, you can fill both of those levels up to some k max, which does not exceed the branch point. And then you would have a solution with both contributions, but the series would converge by the proof that we gave in the last yesterday.
Sorry, I have a stupid question. Couldn't you start with the position space from the beginning?
Yeah. So I think you need a way in, right? You need something which you need something which you can use to infer the large order behavior. So for us in this series of works, or at least in this one paper from last year, the handle we were using was the fact that this dispersion relations have a finite radius of convergence. So knowing that, what does that imply about the position space result? So that's the input we used, and the output we got was about the convergence related to support of initial data. So without that input, I don't know what would be how you would understand the large order behavior, because you need some data about how the transport coefficients behave at large order. So either you just compute them directly, or in our case, we mapped those to the coefficients appearing in the dispersion relation. And since we know how those behave because they end at this branch point, they converge to this branch point, then we were able to use that data to learn about the position space. So if you just want to start with position space in general, you'd have to have some information about the large order behavior of the transport coefficients in order to make progress. Some other information.
Okay, but for example, So even very simple PD, like let's say heat equation, maybe in the K space, it doesn't have a singularity, but if you go back to the X space, it has a pole, right? So it's a kind of, it's a very difficult to know that from K to X or X to K.
So the heat equation, okay, so the dispersion relation is, to keep it in the same language as we've been discussing, the dispersion relation is an entire function.
Oh, it's like d tau minus d square, or
Yeah,
equals something.
So that would have the radius of convergence of the dispersion relation be infinite.
Let's say dx square gonna be just a k square, right? So maybe it can be solvable, right?
Yeah. So in that case, it's a bit different from these examples, because these examples all have singularities in omega as a function of k, and ultimately we believe that's because of causality.
Yeah, I know, but if heat equation having k, maybe it doesn't have the singularity. But if start with the x space, so it has a singularity like a pole in the Bragg plane. So yeah, that's just a small comment about it.
Oh yeah. Okay, I'm not familiar with what happens in that specific case.
I see. Okay. So then I have one final comment before I.
Can I just, or just before your final comment, just one thing? Could you use then the like k max over k star from in your language as a parameter to, meaning in the series where you'd see that when this parameter goes to infinity, you'd have the asymptotic series, and somehow when it was less than infinity, then you'd have different behaviors.
I believe we've only seen, so let's say, factorial growth of the coefficients in the case, indeed, when the case where k max goes to infinity. But I believe we've only seen that in examples rather than proved it. I don't know if my collaborators have any other insight on that, but I think we only showed that in examples, and the thing we showed at the level of a proof is k max versus k star, above or below, with regards to convergence or geometric divergence.
Well, I would say that if k max is finite, you can argue that the spatial derivatives cannot grow faster than a particular power of, like the nth spatial derivative would grow at most like k max to n to some power, right?
So you're saying if k max is finite, we know it's geometric?
I would say so. I think it's impossible.
Do we know for sure that it's factorial when it's infinite?
Okay, I don't have a mathematical proof of that statement. It would, to make such a statement for generic initial data, you would probably have to exclude fine-tuned cases, right? But I would say that that's something that you would generically expect.
Oh, sorry, gotcha. Go ahead. We should probably adjourn quite soon.
I think we can conclude. And the final comment is this. So all these studies of convergence and divergence of gradient expansion of large order behavior and so on and so forth misses a very important feature of hydrodynamics, which is hydrodynamic fluctuations. So in hydrodynamic systems, if you look at the structure of the gradient expansion, the way that sort of I have been writing it, so there's sort of the, let's say, sort of the sound, let's say the sound mode, and then we have some dissipative sort of eta viscous part Q squared, and we say, well, there are cube before, blah, 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 right? If we look at, let's say, the expansion for T mu, this viscous term shows up at the order of Q, because the dynamic equations one more derivative, but they typically have eta times Q in our derivative expansion, and then we're saying, oh, there's a Q squared if you go to second order hydro, and so on and so forth. And we're looking at the derivative expansion, the large order behavior in terms of Q or the sort of component and so on and so forth. But there's actually, there are other terms which go as Q to the 3 house, Q to the 5 house. And these are basically non-local effects that come from the, because hydrodynamic systems are thermal systems, there are thermal fluctuations. And thermal fluctuations do contribute back into the gradient expansion and the propagation of hydrodynamic modes. Okay? You can view this as, so the viscous part is basically transferring momentum through microscopic dynamics, microscopic collisions, and so on. But you can also transfer momentum, dissipate momentum or energy through sound modes. So these are like loops in that language of sound modes. And they do, just like, in field theory, the loops both renormalize these transport coefficients and also contribute non-analytically to the gradient expansion. And they are actually, for instance, they're more important than second order hydro, between first order and second order hydro, between 3 house. And there's, the large order behavior, including the fluctuations, is a total uncharted territories. So in ADS-CFT, these don't show up because they're suppressed by NC. These are 1/NC, but in general, they are there. And so far, I don't think anyone has discussed how do they change the large order behavior, the gradient expansion in general. So that's just a comment, and I would love to understand more how the fluctuations. All right. Perhaps they're analogous to these the normal ones.
I guess maybe we don't have a good model in order to calculate a large order of these. Do you know?
I don't think so. No.
It sounds very difficult within holography.
Yeah, it is very difficult. Yeah, even in ADS-CFT, they're very difficult because these are one of
these are loop corrections in the bulk. Yeah.
But there are these works that couple hydrodynamics to stochastic.
Yes.
So I mean, maybe it's like a stupid idea, but maybe one can, like all these features that one encounters, say in Bjorkman flow, or like in say phenomenologically interesting applications to heavy ion collisions, like they are one way or the other already at the level of the telegrapher's equation. So one can, so this is the equation that Ben talked about yesterday, right?
Yeah.
This damped wave equation, and one can try to to introduce a stochastic noise to this equation and try to see if one can like look at the behavior of large order derivatives of dispersion relations, right? Like basically omega expanded in Q. I mean, like in principle, that should give rise to these like the rational powers of Q in omegas.
Yeah.
And one could also attempt to do linearize analysis of the real space gradient expansion and trying to see what happens. So I mean, I think like one should not probably be concerned about like getting the physics right at the level of a quantum field theory, but try to come up,
No, I mean,
get a bit of an intuition, and then maybe turn to, I don't know, something that is realistic to do, but interesting from the microscopic point of view.
I think that's a very interesting idea. Yeah. So that there are. I mean, of course, there are studies of these sort of nonlinear diffusion type, a little simpler than the telegrapher's equation, maybe because it doesn't have the second order time derivative, but with higher order space derivatives and things like that. I recently have been working on doing analyzing it in a deterministic fashion, so that you can it's similar to like the 2PI kind of field theory language approach, where you can introduce the fluctuations as additional variables to hydro and derive their evolution equations. But even from that to getting to these non-analytic contributions, it's a non-trivial. There's a non-trivial step. So at this point, I mean, realistic or not, I think any example would be very valuable. So yeah, looking at this telegrapher's equation, even at the stochastic level, one problem with the stochastic, the stochastic approach is that the noise. Because the noise is local, its magnitude is proportional to your discretization length, which is at the UV scale. So typically what happens is that these stochastic simulations propagate a lot of UV noise, which sort of eventually gets washed out. But that's a sort of a technical thing. But yeah, I think that's overall something that can be done, perhaps.
I mean, like one thing to be said is that this is not really the effect that is taken into account in at least like in the mainstream hydrodynamic simulations in heavy ion collisions, right?
It's starting now. I mean, so it goes back to the work of so in non-relativistic hydro, it goes back to the 70s, work of Andre and so on. In heavy ions now, there are some groups. I think the McGill group was at their Ohio State group, are sort of implementing some random noise. There's a there are a couple of studies on this nonlinear diffusion problem. Yeah, but it's still fairly new, and it's not as mature as the sort of the ordinary deterministic hydro simulations nowadays.
Like Israel work, right?
Industry, but yeah, there are sort of stochastic codes these days, I think.
Well, I guess, you know, like if I were to single out like one of the most interesting questions, like the question with like the biggest bearing on the field of relativistic hydrodynamics in realistic systems is like the effect of these fluctuations on what we really mean by hydrodynamics, and like how we operate with hydrodynamics, right? Because like the language that has been developed like in the course of the past almost 20 years in the context of holography, you know, kinetic theory, and also like practical applications, like it relies on neglecting these kind of effects completely, right?
Right. Yeah. So
sometimes for good reasons, right? Like for holography, like that's like 1/n.
Yeah, for holography and 1/n in heavy ions, it's there are a couple of things sort of for lower energy collisions in the beam energy scan. That's very important because you're trying to specifically look for fluctuations, look for the critical point, but also that so the separation of scales in heavy ion collisions is in this very sweet spot, in the sense that it's a large enough system where hydrodynamics works, but it's a small enough system where fluctuations are actually not as unimportant as that. Let's say, and if you're an engineer at Boeing and designing an airplane wing, of course you don't care about fluctuations at all. But in heavy ion collisions, especially like in sort of small rapidity windows, are these like extra contributions that people collectively call non-flow, and just subtracted to isolate the signals which are displayed with these V2s and so on and so forth, that match very well with the hydrodynamic predictions, but that part that's subtracted in like small rapidity window could be fluctuations. And of course, this story of long time tails is also like the thing basically. People have been trying to look for a long time, and experimentally, I think still fairly elusive. There are a couple of numerical papers where they observe these T to the 3 house kind of dependence in some numerical simulations. But yeah, it's the literature is fairly thin when it comes to observations.
So do you want to give Alex a chance to grab lunch?
Yeah, that's what I was saying. Sorry, this took a lot.
No, that's okay. That's okay. I was planning to have a quick lunch, so don't worry. Don't worry.
I should actually, meaning as soon as I stop this, my computer will start processing the recording. So I really need to actually stop. Sorry, I will stop now. Thank you, Goche.
Okay.
Thank you for all the discussions, and